Now we turn to the applications of Brownian motion, being the sixth video in the whole motion series, but then under the long playlist for stochastic process. It will be the 47th there. So, and of course, you have a lot of light on stochastic processes following these videos. So, um, first of all, to refresh our minds of the definition of Brownian motion, a stochastic process W of t is called Brownian motion if W of 0 is equal to 0. That's the initial condition. Then you have independent increments, and Wt minus Ws is normally distributed with mean 0 and variance t minus s. And then you have continuous sample parts. So the interpretation is that Brownian motion models continuous random movement over time, continuous random movement over time. So the basic properties are as follows. The expected value of W of t is 0. That's the expected value of any Brownian motion at any point in time is 0. And then the variance, I mean, it's 0 because, it's more like you go up and you come down and you have that canceling effect technically. In a way of speaking, that is, so the variance of of W of t is simply t. So the variance is the time taken. Then distribution is such that W of t is normally distributed with mean 0 and variance t, like that. So mean 0, variance t. That's the distribution. So then talking about the applications, and that's exactly the purpose of this video. So we have application in physics, where we talk about diffusion, like when you spray perfume and you have that spreading over the space and all that. So Brownian motion leads to the diffusion equation, partial u partial t equals d partial squared u partial x squared, where u of x comma t is particle density and d is the diffusion coefficient. An example of that is if a particle follows Brownian motion starting at 0, w of t is normally distributed with mean 0 and um, variance t. So, and then we have probability density function. We have p of x comma t to be 1 over square root of 2 pi t e raised to minus x squared over 2t. So that's the application in physics when we talk about diffusion. So then we have application in finance. Okay. Um, so stock prices are modeled using geometric Brownian motion, GBM, and that is ds sub t equals mu s sub t dt plus sigma s sub t dwt. And if you solve this problem, you get s of t to be s naught exponent mu minus half sigma squared t plus sigma w sub t. So an example of that is this. So given S naught equals 100, mu is 0.05, and sigma is zero point 0.2, then you can say that S of t is 100 exponent 0.05 minus 0.5 times 0.2 squared t plus 0.2 WT. Of course, following all this formula now, and then all of that can be tidied up. So you have application in physics, you have in finance for stock prices, and you have it in applied biology. By the way, when the whole idea of polling of Brownian motion came up when Robert Brown, yeah, Brownian motion, Robert Brown was looking at observing pollen in how pollens were moving inside water. So and he set it so that opened up this whole branch of mathematics called Brownian motion under stochastic processes. So application in biology. Now, your Brownian motion describing molecular motion. So you have mean squared displacement, where you then have the expected value of omega t squared is t. And in physics, MSD will be 2dt in that regard. Then you have application in engineering when you talk about noise. Brownian motion models noise in systems. So the key relation dw to dt gives white noise. So thus Brownian motion is the integral of white noise. So Brownian motion is the integral of white noise. Um, because of course, if this is white noise, right, dwt is white noise dt, so that means integral of dwt is wt, and that will be integral of white noise with respect to t. So I mean, you have all of this in signal processing, telecommunications, and all of that. So, and then we have applications in mathematics. Of course, we're still going to see ito calculus. So for function f of x comma t, So we know that partial f is partial f partial t plus half, partial squared f partial x squared dt plus partial f partial x partial omega t, I mean partial w sub t rather. So this is the noise part of it, now w sub t, or the Brownian motion part of it. So an example will be if f of x is x squared, for instance, and x sub t is wt. So that means that partial f partial t, that'll be zero, that'll be gone, right? Then partial squared f partial x squared, where partial f partial x first of all is x, partial squared f partial x squared, that'll be one, right? So we have one right there. So then dt, so there's no dt, there's no t there. Now all of that will go, but we know that partial f partial x is 2x. Then we have d sub t plus plus the dt that will be coming from here, I believe, like that. So you have that. So this extra dt term is unique to stochastic calculus. So this extra dt, you have it unique to stochastic calculus. So that's ito calculus, which you're still going to see in more depth as we progress under the stochastic processes playlist. And then we have heating time, first passage, which we considered in the last video, I believe. So define tau sub A, that's the time it takes to get to level A for the first time. So that's the infimum, the smallest value of t, such that w of t gets to A, such that the Brownian motion is equal to A. So the key result is that the expected value of t equal to A is undefined. So your Brownian motion will hit any level, but expected time is infinite. So, and then we have random walk approximation. So from the very start of Brownian motion, we already said it that it is the limit of random walk. So as you take several steps under random walk, as the values tend towards infinity, it tends towards Brownian motion. So Brownian motion is the limit of random walks, basically. So W of t is limit as n tends to infinity of summation plus or minus square root of lambda t, delta t rather. So in summary, we then have that we have field and application. In physics, we have Brownian motion in diffusion. In finance, we have it in stock prices, because stock prices are all over the place. If you know something about the stock market. Then biology, you have molecular motion. In engineering, you have noise modeling. In mathematics, you have stochastic differential equations and Ito calculus. In probability, you have heating times. So some key takeaways from this now then is that Brownian motion models continuous randomness. It connects microscopic randomness to macroscopic laws, and it is fundamental in finance, physics, and mathematics. So we can do a quick Brownian simulation, and you see that it comes here. But because it is random, if you take time to be 1 and n is 500, and we do the t is 2 over n. So if we simulate, this keeps changing except if we set a seed. So but if you don't set a seed, each time you run, this changes in shape. I think this is still taking a bit of time. Yeah, now you can see the shape has changed. If you run it again, you have the shape keeps changing like that. Okay, just keeps changing. So practice problems here now. Basic properties. Let W of t be Brownian motion. Find expected value of W of 3 and variance of W of 3. Of course, expected value will be 0. Expected value at any point in time is 0. And variance at any point in time is that time. So variance of W3 is 3. So you want to compute probability that W2 is greater than 1. Of course, you can do that. Then find the distribution of W5. Of course, this will be normally distributed between 0 and variance 5 minus 2, which is 3. Then you want to compute the expected value of WT squared. I think that's T or something like that. Then you have distribution and density, write the probability density function of WT. Then compute this. Uh, I mean, in a previous video, I think I had done this. Then there's covariance and independence. You have all of this. So you want to use Ito's formula to find d of W sub t cube. Then maybe when we get to Ito calculus, we'll talk about it. Then let f of x be e raised by x. Compute d e raised by W sub t. Then verify this. I mean, that we saw this up there from that very heavy formula. Then geometric Brownian motion, which is what you have in finance. So solve this stochastic differential equation. The S sub t equals this. If S naught is 50, mu is 0.1, and sigma is 0.3, write S sub t explicitly. Then compute E of S sub t for geometric Brownian motion. Then talking about heating time, define the heating time T of A and explain its meaning, and so on. So try your hands on this as much as you can, and let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. Okay. If you have subscribed to this channel already, I thank you very much for doing that. And if you have not subscribed, why not do that right away? Hit the subscribe and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That gives you special privileges like having seen some videos exclusively, and of course being the first to see some videos before that see them. You can request for PDF copies of my notes. You can also we can also hang out physically if you're in the same geographical location, or if not, we can hang out online to discuss whatever interests you on this channel, be it mathematics, be it data analysis, data science, machine learning, whatever, scholarships, writing books, anything that interests you at all on this channel, or you just want to have a gist or generally about any kind of ideas. I'll be very glad to oblige if you're a member of the channel, that is. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.